Okay, so welcome to the first ECE 2260 video lecture. Let's see how this works and hopefully things will be okay. I'm going to do my best, and if you give me feedback as I post these, I would certainly appreciate it. Okay, so today's lecture is actually going to be on the concept known as convolution, okay? And essentially, convolution is pretty much how a linear system responds to some input in the time domain. Okay? So we talked earlier that if we given some system H, okay, and you have some input, we'll call this XS, and the output we'll call it YS. Then similarly in the time domain, you'd have X at t, and then out on the output you'd have y at t, okay? And I argued, I think last time I saw you guys, that this could happen in any system really. It can be an electrical system, a mechanical system, or all sorts of systems. Okay, so if the transfer function in the Laplace, or I guess S domain, is going to be Hs, then in the time domain, we said this is the impulse response. It's h at t, right? We did that in the last lab where you had to take the inverse Laplace transform of the transfer function, and we get what's known as the impulse response. Okay? Okay. So, we said in the Laplace domain, you have Ys, Hs multiplied by Xs, okay? However, in time, it's going to be y of t, and then this is where it gets kind of weird. It's this integral form. It's going to be integrating from negative infinity to positive infinity, x of lambda ht minus lambda d lambda. Now you might see that and think like, what the crap, what is that? What does that mean? So I'm going to kind of break this down a bit. So suppose we were to approximate a signal. We'll call this x at t. And we're going to approximate x at t with a bunch of small rectangular pulses, okay? x0 t plus x1 t plus x2 t plus dot dot dot, all the way pretty much forever, really. And so each one is going to be xit, okay? Okay, so we can see this then. If we were to plot this, what it'll look like is we'll have, some curve. It's going to be x of t. And then you have these these somewhat skinny rectangular pulses, right? And they should be uniform in width, but I'm just doing a terrible job drawing them because I'm not on graph paper, but that's okay. Okay. So, say each time point on the left-hand side of each rectangle, we'll say, the first one is going to be lambda 0, lambda 1, so the next one right here. And then we've got lambda 2, that's that one, and so forth. So each one we'll call lambda I for each time point, okay? So then the height at each corner is just going to be x of lambda I, right? So this right here, the height right here, the function, is just going to be x lambda 0, x lambda 1, and so forth, okay? And so essentially it's just the value of x at each time point, right? On the left-hand side of the rectangle, which, we kind of are sort of familiar with this at this point. We did do that lab early in the semester where we did the Riemann integration. Okay, so for each I, in a generic form, we can say, for each rectangle, generically, we can just say xit is equal to x lambda I, right, the height on the left-hand side, multiplied by essentially we have then just shifted step functions. Okay, just like we kind of did earlier in the semester. Okay, cool. And then the gap between each lambda is, we'll call that's delta lambda. So the width for each one is going to be delta lambda. So that makes sense, right? So essentially you'll have a step function here, right? That is ut minus lambda I. And then you have a negative step function here, and that is ut minus lambda I plus delta lambda. Okay, so we end up with this rectangle, and then we end up scaling it by the left-hand side value. Okay, so what we can do then is, now suppose if we let delta lambda go to 0, so it gets really, really small. So the gap between each rectangle gets very, very small. We can say then that we have x of t is equal to x lambda naught times lambda delta times the delta function t minus lambda naught plus x 1 delta lambda delta t minus lambda 1, and pretty much and so forth. Okay, so we can set this up as a big summation then, from negative infinity to positive infinity. We're going from from negative infinity to positive infinity, and so we sum up essentially each of the scaled impulses. Okay. Okay. Cool. Okay. So I'm gonna grab a fresh page. Which I guess one upshot of videos is I don't have to erase whiteboards, which is nice. Okay, so remember earlier we said that if you have a delta function, okay, that goes into our system H, on the output, what we end up with is just H of t, and that again is the impulse response. Okay. Now suppose we have a delta function that's scaled, and so it's getting scaled by x of lambda, x lambda I, times delta lambda, times small delta t minus lambda I, and this goes into our system. So the output, so again, since this is a time invariant system like we talked about last time, so our output is also going to be shifted, right? So it's also going to be shifted by delta I. And the scaling, since it's a linear system, it doesn't matter what the scaling is. So if you double the input, you'll have a double output. And so in this case, we're multiplying the input by x lambda I delta lambda. So the output's also going to be scaled by that. Okay. But what happens, though, this is the actual function of t, this delta function right here. This, and so the output is just going to be the, and if we know a delta function, the output of this system, if you have a delta as the input, is h of t, then on the output we have h of t minus delta I. Okay? Cool. Okay, so now suppose we have a system where we have a lot of inputs. What happens on the output? So essentially then, we have y of t, where you have x lambda delta, delta lambda, h t minus delta, t minus lambda naught, plus x lambda 1 times delta lambda times h t minus lambda 1 plus dot dot dot, and it goes, forever. Okay, so we can set this up then as a summation from negative infinity to positive infinity, you get all these terms. So we've got x lambda I delta lambda h t minus lambda I. Okay, but again, if we let delta lambda go to 0, then essentially we turn it into like a calculus mode. So we end up with y of t equals the integral from negative infinity to positive infinity x lambda ht minus lambda dt. And so this is the convolution integral. Okay. Now, oftentimes it's written kind of in shorthand. We will say that we've got x of t convolved with h of t. So they use this asterisk type of symbol to denote convolution between x of t and h of t. Okay. Now, similarly, we can show that it doesn't matter which way we do the convolution or which order. So we can say that we've got h of t convolved with x of t. Okay. And so then the integral will then be h of lambda x of t minus lambda d lambda. Okay. Okay, cool. So again, with convolution, the order really doesn't matter. We don't care which way we do it. Okay, so let's kind of go back to a visual representation here to show you sort of what's going on. Okay, so just a couple minutes ago, I argued that x of t can be drawn as a bunch of scaled and shifted rectangular functions, or essentially a bunch of step functions, okay? And then I argued that you can also do the same thing with delta functions, okay? So, what we can say then, that if you have, again, there's your x of t, you've got a bunch of shifted and separated delta functions. Again, this is x of t, okay? And the the scaling on each one of these is going to be x lambda I delta lambda delta t minus lambda I. Okay, and we've got a impulse function. Now suppose this is just a generic impulse function, say it's just a decaying exponential. Okay, so we can say then is when we convolve these, okay, I hope you still can see that, and you can, which is great. Okay, so when we convolve these, what we notice then for each step function is you end up with a shifted and scaled copy of our impulse response. Again, I'm drawing these quite poorly, which is fine. So anyway, and then because we are summing them up, you know, whether it's a discrete sum or a actual integral, what we end up with is we end up with kind of the function of the big hump. It looks maybe something like that. Okay, so that's what y of t looks like. Again, and this is a very gross approximation. Okay. Okay, cool. Yeah, so let's do an example, kind of an analytical, I guess an analytical integral form of this. Okay, so I'm gonna move these sheets out of my way, store those. How many time? 15 minutes into this. Okay, cool. So consider, again, this is a very basic example. So consider we have a impulse function of a system. It's going to be e h of t is equal to e to the minus t ut, okay? And we've got x of t is going to be, I don't know, just a step function, okay? So essentially, I don't know, you can think of this just as a very basic like RC circuit. Okay, the RC circuit would have a very similar impulse response, and then this would be like a step input, essentially. Okay, so we have y of t. Okay, so we're going to set up that integral. So y of t equals integral from negative infinity to positive infinity u lambda e to the minus. Now again, if you look at the convolution, remember you had h of t was t minus lambda, right? And so you need to replace all the t's in h of t with t minus lambda. So you have e to t minus lambda u t minus lambda d lambda. Okay? Cool. Now what's interesting about this is we notice right here that this step function is, well, this one, it's only non-zero where lambda is greater than 0, right? So if lambda is less than 0 in the step function, then the step function goes to 0, which means the whole integral goes to 0, right? Similarly, we have the same thing here, where if we've got t minus lambda, so t minus lambda must be greater than 0 for it to be non-zero, okay? So t must be greater than lambda. So what this suggests then, that we can simplify this down quite a bit, and we can say that we're only integrating lambda. Oh, no, I made a mistake, I'm sorry. Sorry, this should be d lambda, according to the original form. Okay, so we're only integrating across lambda, right? And so we're integrating from 0 to t. And then at this point, it's a pretty straightforward integral. It's pretty easy. Okay. So there's one more caveat, though, I need to mention. And that t, for this step function to be greater, to be non-zero, this one right here, t must be greater than lambda, right? But that also implies, because lambda must be greater than 0 for this case, then t must also be greater than 0. So we can multiply the whole thing, the whole integral, by a step function to kind of show that behavior. Okay, so we integrate, and we're going to divide. Make sure I get this right. Oh, no, I screwed this up. Okay, let's simplify the integral first before I mess this up before I botch this too badly. Okay, so what we're going to do is we are going to, since we're integrating over lambda, I can pull this e to the minus t out. So we're integrating from 0 to t, e to the lambda, d lambda. Again, so the whole thing's multiplied by ut. Okay, so the integral is super easy, it's just e to lambda, and we're evaluating from 0 to t, and the whole thing's multiplied by ut. Okay, so we have e to the t, and then we've got e to the t minus 1, right? ut. Now this can simplify then quite a bit. So if we distribute this e to the minus t into that expression in the parentheses, what we end up with is just going to be 1 minus e to the minus t ut. Okay, cool. And so that's how we can do this analytically, okay? Now, there are two ways we can approach these. One, we can do analytically, and the other is we can do it graphically, or sort of graphically. Okay, so to do that, let's plot. So we've got, this is h of t, right there. That's t on the x-axis. So these are the functions that we are convolving, okay? Okay, and so this is the decaying exponential, and this is just a step function. Okay, so what we can do is we can draw the whole thing where t equals 0, right? So if t equals 0, we have two functions we need to be concerned about. So we've got, in that case, remember it's 0 minus lambda, because the expression in the integral is going to be h of t minus lambda, right? So we let t equal 0, we can plot it, and we're going to plot against lambda, actually. Okay, so the expression, so that function then, what it looks like is going to be e to the lambda times u minus lambda. So it's kind of, it's sort of flipped, right? So it's a rising exponential, but it's been flipped. So we only care about the stuff where lambda is less than 0. So it looks like that, okay? Okay, so that is h of 0 minus lambda. Now for u, so for x of lambda, well, x of lambda doesn't change, right? So we just have u lambda. And so that's just a step function. Okay. So this method, this graphical approach, is often called the flip and drag. Okay. Ew, not flag. We got flip. Okay. So we did the flip part, right? So we took what would normally be a decaying exponential, and we just flipped it across the y-axis. Okay, and now we're going to start to drag. Now we notice that any time where t is less than 0, what happens is the x lambda doesn't move, right? Because x is purely a function of lambda, and so nothing changes there. However, we can see that h of t minus lambda does change. What happens where t is less than 0, it starts moving to the left. Now in this instance, we can see that this, so here we got h of t minus lambda right here, and that's kind of drifting leftward. So what happens then, if you look at the convolution expression again, you have x of t multiplied by h of t minus lambda, right? So if you multiply it all out, you've got nothing, okay? Because x of lambda times h of t minus lambda, there's nothing going on. So the whole thing is 0, right? So again, I'm plotting h of t minus lambda and x of lambda, okay? So the whole thing's 0, and you integrate, and then what's interesting then is it's 0. So y of t here is going to be 0 where t is less than 0. And we already showed this analytically why that's the case, but this is another graphical representation of that. Okay, cool. So what we can do now is we can start to drag it to the right. So we started dragging it to the left, and we saw what happens is you start dragging h of t minus lambda to the left. Nothing, there's no overlap between the two parts, and so you end up with 0. Now suppose you start dragging h of t lambda to the right, what happens? Well, suppose we drag it to t minus 1, okay? So here, what I'm going to do, again, so this is x of lambda. X of lambda never changes. But here what I did, this is h of negative 1. Sorry. That is 1 minus lambda. Okay, so it gets shifted rightward once. Okay. So we can see that when you multiply these together, what you end up with is anything, you know, where there's no overlap or interaction or whatever you want to call it, like all this stuff, that all gets canceled out, right? It goes to 0 because the, you know, h of 1 minus lambda is 0, where lambda is greater than 1, right? And similarly, on the left-hand side, anything where lambda is less than 0 goes to 0 as well. So essentially what we end up with when you multiply these two together is we just end up a little bit of space, a little bit of function right there, okay? So what I'm doing is I'm plotting x of lambda multiplied by h of 1 minus lambda against lambda, okay? Anyway, and so here, then you just integrate, right? So this is y of 1, and then if you were to actually work that out, what we end up with is it's 1 minus e to the minus 1, okay? Okay, cool. So, yeah. Let me grab some fresh paper real quick. Okay, so now let's do a case where well, actually I'm going to use this paper a little bit so you can kind of see where we were, because that's one upside to this video stuff. Okay, so now we're going to let t equal 2. Okay, so where t equals 2, again, so now, again, x of lambda doesn't move at all, but h, lambda moves 2 to the right. So now we have h of 2 minus lambda. Okay, that's lambda right there. Okay. So you multiply them together. Okay, and then you integrate. So essentially with convolution, what you're doing is you flip one function. Okay, in this case we flipped e to the minus t ut, and then you start dragging it. And for each incremental drag, every time you move it, you end up needing to multiply the two functions together and then integrate, okay? So here, and so this would be y of 2, this would be equal to 1 minus e to the minus 2, okay? Okay, cool. Now, if at this point you are feeling kind of lost, don't lose hope. Don't feel too bad about it, because honestly, convolution is one of the hardest concepts in maybe electrical engineering. It takes a lot of people a lot of time to really get the hang of it. And unfortunately, without your feedback in a video or not being in a live setting, it's hard for me to kind of gauge where people are at. So, and I'm also going to post a bunch of other YouTube links where people have explained convolution. There are a million out there. You can definitely take a look, watch them, and hopefully between my explanation and others, you will get a better sense of how this actually is working. Okay, cool. So let's do example 13.3. So now we're going to see this in action, okay? So suppose we've got a circuit with some arbitrary input voltage, okay? Inductor and a resistor in series. So essentially it's a very, very basic RL circuit, nothing crazy. In fact, they make the values really easy to work with. And what we're going for is the voltage over that resistor at the end, okay? Okay, so what they give us though, they give us a really weird input voltage, okay? So essentially, it's going to rise, I think it's the first 5 seconds, to 20 volts, and then it just stays steady state, you know, flat line from there on out. Again, this is our input voltage, a function of time. Okay, cool. So I guess if what we want to do is find V out here. So there are two approaches to this. I'm going to show you convolution, then I'll show you what I consider actually the better approach. You guys can be the judges which one you prefer. I have a pretty good idea what your answer is going to be, though. Okay, so the first thing we do, I guess step one, is we're going to put into S domain, and then we're going to find the transfer function HS, right? Okay, so the transfer function is going to be pretty straightforward. It's going to be just V naught VI times 1. It's a voltage divider, right? So it's going to be 1 ohm plus S. Or I guess a simpler way of writing that should be VI over S plus 1. Okay, so then H of S is going to be 1 plus, or S plus 1. So the next thing we need to do is we need to find the impulse response, H of T. Okay, so H of T here is going to be the inverse Laplace transform of the transfer function again, HS. And that's just going to be e to the minus t ut. Okay? Okay, cool. So the last thing we need to do then, oh yeah, so that's the same impulse response as last time, just happened to be. So now to find the output, we're going to do the convolution. Okay. Cool. So we know VIT, we know H of T, we can do the convolution integral. Now this convolution is non-trivial. It's actually it's kind of tricky. But that's fine. So it's going to be kind of the way I'm going to set this up, and similar to the way the book would do it, I'm going to kind of do this sort of piecewise. And I'm going to do it sort of almost as a hybrid of the graphical and the analytical integral approach. Okay? Cool. So what we can say then is we're going to flip VI, okay, and we notice, again, I guess we'll say this is at time t equals 0, okay, so VI gets flipped, as does, but we'll call this VI nega lambda, but the H of T, we didn't flip H of T, okay. So we left that one. We flipped the input voltage. We left the impulse function the same. You can choose which way we want to do this. It doesn't matter, really. I'm fine with whatever. Yeah. But we notice, though, at any time where we multiply these two functions, that if time is less than or equal to 0, when you multiply them together, what we end up with, essentially, is 0, pretty much for all lambda, right? Again, we're graphing against lambda. So because of that, yt is equal to 0 for all time less than or equal to 0. Okay. Okie dokie. So then what we can say then is now, again, we flipped the input voltage. And the decaying exponential, the impulse response, we left the same. But then no, I don't like that. It's ugly. But then we started to move, so we flipped the input voltage, and we're going to start to move it rightward a little bit, to see what happens, okay? Cool. And then we noticed that if we, as we increase the shift pretty much from 0 to t less than 5, okay, we kind of have a similar response. Essentially, you're multiplying a pretty much linear a linear slope, okay? Okay, so you can say then that what this would look like in an integral form, you'd end up with v naught of t. Okay, so we're going to be integrating here from 0 to t, right? So we're integrating from here to how much this has been shifted over, which happens to be t. Okay, and then this is going to be 1 minus, or sorry, t minus lambda e to the lambda, or e to the minus lambda d lambda. Again, this is h of t minus lambda, or sorry, that's x of vi t minus lambda. Okay, cool. Okay, so we can simplify this integral quite a bit, and it generally kind of sucks, to be honest. You have this integral, which is fine. That's just a norm. We can take the 4t out in front, but this one, on the other hand, is not as straightforward. So this is going to be 4 lambda e to the minus lambda d lambda. That's going to require integration by parts. I'm not going to spend the time to do that. You guys can, it's fairly straightforward integration by parts. It's just more tedious than anything. So we end up with just 4 e to the minus t plus t minus 1 volts. Okay, cool. So this is the expression for the output voltage from time 0 to 5. Okay, so next we need to kind of look at what happens as we kind of start moving forward even more. Okay, so here we kind of start shifting the input voltage further to the right. Again, this is e to the minus lambda u lambda. And here, again, this is going to be, the input voltage, or the expression for the input voltage, t minus lambda. Okay, so we start increasing t, so start shifting rightward a bit. Okay, and again, we're plotting against lambda. Okay, so we can set this integral up. We notice that this is valid from, there's not much change from 5 here to 10, okay? So we can say the output voltage is equal to 0 to t minus 5. Okay? Because what we're doing right here, so this first part, we're going to be integrating from, we're going to be integrating for the whole thing, right? From here to t, right? But we got to do sort of piecewise. So we're going to go from 0 to t minus 5. That's going to cover this rectangular bit. And so we have 20e to the minus lambda d lambda plus, and then we go from t minus 5, which is right here, all the way to t minus 5 to t, and that is going to be 4t minus lambda e to the minus lambda d lambda. Again, fairly straightforward. This is a bit more, this is trickier. And what we end up with, and just is a spoiler, 4 times 5 plus e to the minus t minus e to the minus t minus 5 volts. Okay. And again, I set up the integrals. You guys can go and work this out on your own. Okay. So I guess the last case we need to sort of be worried about is where the input voltage gets so far shifted to the right, there isn't any part that's less than lambda equals 0. Okay. So this is, I guess, valid for time t greater than 10, because if you shift it greater than 10, then all of a sudden they're both completely overlapped. So we've got the output voltage is equal to t minus 10 to t minus 5, which again is covering kind of the rectangular area. Oh, I just realized. Okay, I'm going to have to clip out a good amount of this. Whether or not I actually go back to the video and screw it up, or manually clip it, or just flag it, I'm not sure. Okay, let's rewind. Last 5 minutes. Okay, so you were able to see me working on this portion right here, where time t equals 0. Where pretty much any time where it's less than 0, yt is equal to 0. That's fine. So now let's see what happens where you start shifting the input voltage rightward a bit. Okay, so you got e to the minus lambda, e lambda, and then how much we shifted is just t, right? Again, this is the input voltage, so this is vi t minus lambda, and we're plotting its lambda. Okay, so we can set this integral pretty much such that we have the output voltage v naught t that's equal to the integral from 0 to t for t minus lambda e to the minus lambda d lambda. Okay, this integral is going to require integration by parts. So we've got 4 t e to the minus lambda d lambda minus 0t 4 lambda e to the minus lambda d lambda. Okay, so we can see that one's not going to require integration by parts. We can just take this, move it out front. This, on the other hand, we would require integration by parts. I'm not going to take the time to do that. Just you guys can do that on your own. It's a good exercise. I'd recommend it. Okay, and so that's the expression for the output voltage. And this is valid from 0 to 5. Now the question why I say 5 is because once this has been shifted over by 5, then at that point, you'll see in a second, once we do 5, then all of a sudden this corner starts passing over. And so we kind of have a different expression going on right here. Okay, so we need to set up a separate integral for this. Okay, so we are integrating. We're going to do this by two pieces. First piece, we're going to have to integrate from 0 to t minus 5, which is right here. Okay, so if this is t, we're going to go backwards 5, and that's right here. Okay, so we multiply these two functions. Okay, to do the integral, so now the integral is 20e to the minus lambda d lambda plus t minus 5 t for t minus lambda e to the minus lambda d lambda. Okay, so this actually, when you actually do these integrals, it winds up being 4 times 5 plus e to the minus t minus e to the minus t minus 5, and that's volts. Okay, And again, this is valid for 5 to 10. Now, I showed earlier why 5 on the lower bound, but for 10, why I chose 10 is once we hit 10, the time shift to 10, then all of a sudden this lower bound right here has passed the y-axis, the 0 point, essentially. So we can set the integral one more time. Okay. And so we're integrating for this point from t minus 10 to t minus 5, 20e to the minus lambda d lambda plus t minus 5 to t for t minus lambda e to the minus lambda d lambda. Okay. And then this is going to be equal to 4 times e to the minus t minus e to the minus t minus 5 plus 5 e to the minus t minus 10. That's volts. Again, this is valid for t is greater than 10. Okay? Okay, so now we have these expressions. If we were to plot all of this, I'm gonna kind of do a cheap plot, and there's a better one in the book. I'd recommend you guys take a look at it. Okay, so it's at 5, at 10. So you can see that the response is gonna look something like this. Again, this is what the input voltage looks like, these dashed lines. The response, on the other hand, is going to be kind of almost like curved in a way. So that's the response. And this is the excitation, okay? Or rather, the input voltage. Now, I want to make a quick comment. Okay. There's an alternative way of doing this. Okay. So what you can do is you could set it up such that we know HS, right? We solved that initially. So we also know that the output of a system, YS is equal to HS XS, right? So that would also mean that the output voltage in the Laplace is just the transfer function times the input in the Laplace, okay? So we know what the transfer function is. It's just 1 over 1 plus s. And so if we were to take that input, that crazy input, and then take the Laplace transform, we could just do the whole thing in the Laplace domain and avoid the integral. It's not the easiest Laplace transform in the world. You'd have to do it in steps, but it might be easier ultimately. So maybe a great question would be to do a problem similar to this, but I would have you do the integral in time domain using convolution, and then also you could do it in Laplace using Laplace transforms as well. And ideally when you finally found the output voltage in time, they should be the same. Okay, cool. Okay, so just a few more comments about this. We can say that circuits actually do have memory. And the basic idea here is the current output. When I say current, I'm not saying electrical current. I mean like current in as far as time. Like it's currently, like 4 o'clock when I'm recording this. So the current output relies on prior input. Okay? So memory, or I guess in this case, lack thereof, is how much output matches input. Okay? So in a way, you can say that h of lambda is a weighting, it's a weighting function. Okay? So suppose we've got a system, h of t, and it's just a times delta t, okay? So if we have our output, y of t, we've got h lambda, delta t minus lambda d lambda, okay? That's equal to minus the integral from negative infinity to positive infinity, a delta lambda xt minus lambda d lambda, okay? So this just turns into a sifting problem, right? I mean, so I can pull that a out, right? And then what I do is let the t, you know, we can say that delta lambda is the same thing as lambda minus 0, okay? So we can let t be 0, and so we can, we can put lambda be 0, so we can pull out the x of t, and then just integrating over this delta function. And so we end up with just a scaled version of our input. So this system has no memory, okay? Because it's not relying on no memory, because it's not relying on prior inputs. It looks exactly like the actual input. Okay. Okay. So the last concept I want to go over today is sort of impulses in real life. Okay. So suppose we've got a circuit and it's just two capacitors and a resistor. And what we're interested in is the current through this loop. Okay, that's C2, that's C1. Now C1 is actually initially charged by some initial voltage, V naught. Okay, so if we were to take this and put it in the S domain, what we'd end up with is a capacitor in series with a voltage source, okay? You have a resistor, you have 1 over SC2, and you have a current flowing through, okay? Okay, cool. So if we solve for that current, then it's essentially just the voltage, V out over S, or V naught over S, sorry, over all these elements in series. So you have 1 over SC1 plus R plus 1 over SC2. Okay. And I'm going to simplify this a bit. I'm going to multiply top and bottom. I'll just write out. So I can multiply top and bottom by S, and then I'm going to divide by R. Okay. S divided by R. So what we end up with then is V naught over R all over S plus 1 over R. And we'll say this is C equivalent, where C equivalent is just the capacitors in series. So that's C1 times C2 over C1 plus C2. Okay. So we've got the current IT is going to be V naught over R, e to the minus t, R, C, the equivalent capacitance. And again, UT. Okay, so what happens? Well, now we're going to let R go to 0. Okay, so if R goes to 0, then we have a huge current spike, right? The current is essentially going to go to 0, which we see right here because we have R in this denominator. Okay. Similarly, if we want to integrate over the whole thing, and essentially what that'll do is we'll end up getting the whole charge. So we're integrating from 0 minus to infinity, V naught over R, e to the minus t, R, C, E, dt. And if we do that, we do this integral, and then we let R essentially go to 0. Well, we end up with it just V naught CE. Okay. Which is cool because we notice right here, this essentially looks like an impulse function because the current's going to infinity, yet we end up with just scalar on the output, right? As we integrate over it. So we can say in this case that IT is equal to V naught CE times a delta function, okay? Again, that's valid as R goes to infinity. Okay, cool. Okay, so that's one way we can look at it, sort of approximating an impulse function in a circuit. Now, we can also kind of look at it using an inductor. Okay. Ugh. So in this case, we're actually going to use real numbers, sorry. This is 100 volts. And we're going to draw it first in time domain. I'll put it in S domain and take a look. Okay, cool. And we're going to look at the output voltage right here. Okay. So what we can do then is we can put it into the S domain. So we've got (100 over S). Okay. 3S, because we had an initial, and then this, we have a switch that's going to open at time t equals 0. Because we had an initial current flowing through that inductor, we need to include a source for that. So that's so that's going to be just 30 volts. The other inductor, on the other hand, did not have a source going through it, and so, or sorry, an initial current going through it, so we don't have to include a source for that. This is 10. Okay, cool. So we can just solve for V out at this point, okay? Okay, cool. So there are a lot of ways we can do this to solve for V out. The book actually, when you follow their logic, they use a node voltage, which is fine. I argue that it's a lot easier just using a voltage divider, because that's essentially what this is, right? So we have two voltage sources in parallel, so that just, or sorry, in series, that's 100S plus 30. And then the impedance we care about, or the voltage we are interested in, that's 15 plus 2S. Okay. And then we've got a bunch of stuff in series. We have 10 ohms plus 3S plus 15 ohms plus 2S. Okay. So what we can do then is we can just start factoring everything out. And so we end up with 1500 over S plus 450 plus 200 plus 60S. And that is all over 25 plus 5S once you combine all that on the bottom. Okay, cool. So what I'm going to do is I am going to divide top and bottom by 5. And I'm going to multiply top and bottom by S, so I can clear that S right there. And I'm going to get rid of that 5 in front of that S on bottom. Okay. So what we wind up with is going to be 12S squared plus 130S plus 300 divided by S squared plus 5S. Okay, cool. So now we can just do partial fraction expansion to put this back into time domain. Okay, so we got to get into a good form to work with. So here we have to use a bit of long division, which is never fun, but it's helpful. Okay, so we have 12S squared plus 130S plus 300. Okay, so we have 12, so we end up with 12S squared. That's going to be 60S minus. So we have 70S plus 300. Okay. So V out is going to be 12 plus 70S plus 300 over. I'm going to pull an S out of that just so we can kind of see the roots a bit more easily. S times S plus 5. Okay, so this is just a very classic, real and unique partial fraction expansion. Nothing tricky. So I'll do the partial fraction expansion just so we can practice a bit. So we end up with 12 plus K1 over S plus K2 over S plus 5. Okay. So K1 is going to be S times the V out. It's S equals 0. Okay, and so that's 60. Okay, if you plug everything in. Okay, so then K2, on the other hand, is going to be, we'll have S plus 5 times V out, S equals minus 5. And then we just end up with just 10. Okay, so then finally we end up with 12 plus 60 over S plus 10 over S plus 5. We know the inverse Laplace transforms for each one of these. It's pretty straightforward. So now we have V out T equals 12 delta T plus 60 plus 10 e to the minus 5t ut volts. Okay, now what's interesting here, guys, that's kind of cool is what we wind up with is we have a delta function that shows up in our final answer. And that actually does make sense, because if you take a look at this sort of from a current perspective, okay, let me get the book and pull the pages. We'll use the book to kind of look at this. Let me flip to that. Okay, cool. Okay, so suppose we are interested in I1 and I2, okay, and we want to find the final current after the switch opens, right? So what would happen is initially I2 is going to be 0, but there actually is a current right here for I1. So what happens is if you were to take these and then solve for I using inverse Laplace methods, what you end up with is you actually end up with a an expression right there. But what's interesting is you have I1 and I2, but they end up combining and jumping up to 16. So to make that jump happen, so you have this like stepwise jump. Now we know the voltage in an inductor is going to be the derivative of the current, right? So if you take the derivative of this current right here, we notice we have a step function, which is kind of cool. Or sorry, you have an impulse function when you take the derivative of this sort of step response, which ends up matching the math we just worked out. Okay. Okay, and then yeah, and then kind of the last thing I want to mention then is this idea of an impulsive source. Okay, so the basic idea here, if you have a circuit just an RL, you can have a voltage source that's an impulse. Okay, most of the ones we've dealt with so far have been step functions or step responses, but you can just throw an impulse as your input. That's gonna be kind of tricky if we were to do that in lab, just because our function generators, how do you program an impulse into a function generator? But fortunately, actually, there is a way to sort of mimic it, and we'll play around with that next semester in one of the labs, assuming that we all end up going back to campus at some point in our lives, which I think we will. Anyway, so yeah, that's kind of all I wanted to go over today. I guess one more thing I guess we can do is, if you have an impulsive source, you take the Laplace transform of the circuit. What we end up with is you have SL and R, just like you normally would. But here, it's just V naught. You don't have, because if it's a step response, it's usually V naught over S. But if an impulse response, it's V naught. So that's something we got to sort of be aware of. Okay. Yeah, so that's pretty much all I have today for this lecture. Like I said, video is certainly not the best way to explain convolution at all. It's really kind of a hard subject to begin with. So I would encourage you guys to please read the book section on this, and then I will post some links to what I consider to be helpful YouTube videos where they also explain it. So you'll see it in a few ways. Cool. So yeah, thanks for slogging through this video, and yeah, we'll see you next time.